Okay, so last time we have seen the slope stability for infinite slope, in which up till now we have considered two cases: the stability of infinite slope for cohesionless soil, and then we have taken the stability of infinite slope for cohesive soil, or you may say it is a c-phi soil. Then in the last lecture, we have seen several examples for finding out the stability of infinite slope in various soil conditions. Then after, we are moving to stability of finite slopes, and in finite slopes we have seen there are various types of failure, mainly phase failure and the base failure. In the phase failure, we have categorized this failure into the two parts. The first is a toe failure, and second is the phase failure. And in the base, and the third one is the base failure. So if my slip circle is within the face of the slope, I would say it is a phase failure. If it is extending up to the toe of the slope, we have said it is the toe failure. Similarly, if our soil below the base is weak, in such situation, the slip circle or the failure of the slope may extend to the base of the slope, and in such case, the base failure may occur. Then after, we have seen various types of failure surfaces. Mainly, we have seen three types. One is planar failure surface, then the circular failure surface, and the non-circular failure surface. And we have seen under which conditions this planar, circular, as well as the non-circular failure happens. If I just give the recap, the planar failure will occur in the case of if the soil is having a stratified deposits. In such situation, you will find various planes. The failure of the slope will happens in the planes. Similarly, other is the circular failure. That is also we have seen. Mostly we are assuming that our slope will fail in arc or in a circular surfaces. And third part, which is the non-circular surfaces, which is maybe a combination of planar as well as the circular surface together. So this is the three types of failure surfaces also we have discussed. And then we moved to this particular side, which is the method of analysis of finite slopes. Mainly, the stability of finite slope is investigated by number of methods. Like first is Kalman method of planar failure surfaces. This method will assume the failure surface which is in planar mode. So basically, it is being utilized for stratified deposits. Second is a most common and widely used method for analyzing the finite slope, which is Swedish slip circle method. Today we are going to see this particular method in detail. Third method, which is called as the friction circle method, and the fourth method, which is the Bishop's method. In your syllabus, we are going to put this particular method, which is second and third together, right? Rest of the method is just for the information. Let us see what is a slip circle method of analyzing the finite slope. The method is developed by the Swedish engineer, assumes that the surface of the sliding is an arc of the circle. So he has assumed the circular failure of the slope. We can consider two cases for such failure. First is the analysis of slope, finite slope in pure cohesive soil. So in this, I am considering the value of phi is equal to 0. And in the second analysis, I will consider the analysis of finite slope possessing both cohesion and friction. It means I am going to consider the c-phi analysis, which will be applicable for all the types of soils. Let us see the first analysis that is applicable for clay soil or a pure cohesive soil where phi is equal to, or the effective value of phi u is equal to 0, and that is why this analysis has been called as phi u analysis. Now let us understand what is exactly this analysis means. Now let us consider the slope, which is this AB. You can see on the slide, this is the AB is the slope I am considering. The stability of this particular slope is to be determined. The method consists of assuming number of trial slips. Like for example, if you see, this is a trial slip that is I have assumed. You can assume number of such trial slip. For a trial, I am assuming right now, this is a trial slip at which the particular failure of the slopes may occur. And I need to find out the factor of safety of this particular trial slip. The circle corresponding to minimum value of factor of safety is known as critical slip circle. If I summarize this particular thing, like if you want to analyze this particular slope, what you need to assume is, you need to assume number of such trial slip, because you don't know from where this particular slope will fail. It may fail from here, it may fail from here, it may fail from anywhere. And so that you need to assume number of trials, and this trials, so you can say this is as a trial or this may be as a trial. So for a time being, I am assuming this is a first trial, and for each trial, you are going to find out the factor of safety of that particular trial slip. When you analyze this factor of safety, the trial slip which corresponds to minimum factor of safety, which is called as the critical slip circle, means from that particular slip circle, the slope is in the verge of failure. Let us see. Let AD is the trial slip circle with a radius R, and O is the center of rotation. You can see this is the trial slip circle we have assumed, which is AD. This D should be here. AD is the trial slip circle. That is what we have assumed. And this I'm just putting, you can say, the random location for this particular center. And I am putting, you can say, this radius with small r. We will take, you can say, the more detail how to fix up, you can say, this particular center, which is later on. At present, just assume this is the O is the center. From this particular center, I'm taking randomly, and from this, I'm drawing a trial slip circle with a radius r, and this r will actually change with respect to number of trial slip circles. Okay, let's do the analysis for this arc only at present, just to formulate the sequence. Now, once you form this particular trial slip, let W is the weight of soil of wedge ABDA of unit thickness acting through the centroid. So I need to find out the weight of this particular trial slip circle ABDA, right? So that is, I'm assuming that is a W, and this weight will act at the centroid of this particular trial slip circle, S, I'm assuming two-dimensional problem or the plane strain problem. I am assuming thickness towards the z-axis, which is a unity. Fine. Let us go further. Now, if you find out a driving moment MD, which particular moment which drives the force towards the failure, then this driving force, which is with respect to the location of the center of trial slip circle, which is O. So I am finding out the moment of this with respect to center O, and which is nothing but the driving moment, which is equals to W. And if I'm assuming the distance from this is x bar, which is nothing but the centroid distance with respect to this. So if you find out this x bar and W, then this is a clockwise moment, which is W into x bar, where the x bar is the distance of line of action of W from the vertical line passing through center of rotation. Now, let us go further. If the CU, which is the unit cohesion, and L arc is the length of trial slip circle AD. This is the L arc. If you take this length, then this is nothing but it is the length of slip circle. Now, if you find out L arc, which is nothing but 2 pi r into delta, you can see this is the angle is delta. So I want this arc. So total circle is the 2 pi r. So I will take 2 pi r delta, divided by 360. So I will get the length of this particular arc. Now, if I see this is the arc is 2 pi r delta divided by 360 degree, and L bar is crossing in this way. So if I see this particular cohesion of the soil which binds the particle here, you can see this is the soil, and if this is a driving force is acting towards this direction, and I'll just put it, you can say some pointer, so you will see. Okay. You can see this is the driving force. You can see this in this direction, this driving force will act, because what we are finding out, the MD, which is nothing but WX bar, which is in this direction. But because of the cohesion into the soil particle, which resists the force in the reverse direction because of this CU, right? So CU will be the resisting moment, and resisting moment which is acting along the length of this particular arc. And so that if I say it is a shear resistance which is being developed, shear resistance is developed along the slip surface, which is equals to this CU which is acting on this surface multiplied by the length of the arc, which acts at a radial distance r from the center of rotation. You can see this is the radial distance r, right? So if I take again the moment with respect to point O, then this will be, you can see this mr, which is nothing but the force, which is nothing but Cu into L bar, which is my resisting force, multiplied by the distance, which is r. So this will come Cu L arc into r. Now, as you know, the factor of safety is equal to resisting moment to the driving moment. You already find out both the parameters, so just put these values. So mr, we have said Cu L bar into r divided by W into X bar. So this particular thing will give you the value of factor of safety. It's very, very easy. Just here, if you see all the parameters is with you, like cohesion, which is the soil parameter, L arc, you can find it out with respect to the formula, which is 2 pi r delta upon 360. R is the radius, whatever the radius of the slip circle that you are assuming. Similarly, W and X bar that you need to find out. Since this is the irregular figure, we are going to use a different mathematical ways to find out the value of W, which we will see later. Alternatively, if I take Cm, which is the mobilized shear strength of the soil, which is necessary for equilibrium. So in that case, so Cm, when the shear strength will mobilize, when the slope is in the verge of failure, at that time, whatever the value of cohesion is there, it is being called as mobilized shear strength or mobilized cohesion. So when I am saying the slope is in the verge of failure, it means the factor of safety should be equals to 1. So if I put the 1 in this equation, then you will get Wx bar is equal to, C is going to replace with the Cm because your cohesion is already been mobilized because the slope is in the verge of failure. So in that case, the Cu will replace by Cm into L arc into R, so that you can find out the value of mobilized cohesion by respect to this formula. So just take, you can say this here, and you will get this value. Now, if you want to find out the factor of safety in relation to the cohesion, since the phi parameter in this particular type of soil is 0. So Cu, which is my undrained cohesion before failure, and the Cm, which is my mobilized cohesion, when the slope is in the verge of failure, which is equals to whatever the value that you have find out, where the distance x bar is the centroid of the wedge, as you have seen, sent from the center of rotation O, and it can be determined by dividing the wedge into number of vertical slides and dividing the algebraic sum of moment of weight of each slide by the weight of wedge. We will see this, how this will evaluate it. Now, if you take since this is a cohesive soil, there is a chances, as you have seen in the case of earth pressure theories, we have seen if you have a cohesive soil, there is a possibility that the tension crack which will be appear at the top, and at that particular, when we are seeing the earth pressure theories, we have derived this particular depth of tension crack, which is nothing but Z0, which is nothing but 2c by gamma. Up to certain depth, the tension crack will actually going to develop, and that depth is nothing but 2c upon gamma. Now, through this particular tension crack, the water will seep into the crack, and which exerts the hydrostatic pressure, that is Pw, in the portion dE, which is nothing but the height Z0 by 3 from point E. So you can see, sorry, if you go back to this slide here somewhere, so from here the tension crack will going to be developed here, and that depth is already been put. However, the analysis will stand the same even in this case, because the tension crack will not hamper the overall failure of the slope. So modified arc is also the similar, which is equals to what we have derived in the equation number 23.16, which is nothing but this, which stands same, which is with respect to mobilized cohesion, because when the slope is in the verge of failure, it will actually mobilized, right? So the equation will remain same. Okay. So this is what the analysis in the case of cohesive soil. Now let us take the second analysis, which is for c-phi soil. If you have any questions in this, please post in the chat. So at the end of the lecture, I am able to answer it. Okay. So please let us take, you can say the second, you can say the analysis, which is c-phi analysis. In order to test the stability of the slope of c-phi soil, the trial slip circle is to be drawn. The material above the assumed slip surface is divided into number of vertical strip or the slices. I will just show you how it has been done. You can see this already we have seen, you can see in the last thing, like for example, what you can do is, this is my slope that is to be analyzed, and which is made up of c-phi soil or a cohesive soil, doesn't matter. While let us draw a trial slip circle with the random center O, because right now we have not fixed a method to find out what is exactly the location of this particular center. So at this time I am assuming is you can see the random center, and I will say that this is what my trial slip circle I have drawn, and I'm assuming that the slope is going to fail along this particular slope. Under this, now what I'm doing is, once I will find out this, I will divide this particular slope into the number of trial slip. So you can see this 1, 2, 3, 4, 5, 6, 7, 8. This is the divisions of the slope into the number of segments. Now let us go further. The forces between the slices are neglected, and each slide is assumed to act independently as the column of soil of unit thickness and the width B. Please see carefully. The forces between the slices are neglected, and each slice is assumed to act independently as a column of soil with unit thickness and width B. I will again go back to the figure. You can see this particular slides what we have drawn. I am assuming that the force between all the slides are neglecting. Of course, there will be a shear force which will be act if you take such type of columns, but I am assuming there will not be any force. And the second, I will assume this each slice will act is having, you can see the unit width B and having unit thickness, and it will be acting independently as a column of soil. Now let's go further. The weight W of each slide is assumed to act is at the center. So for example, if I draw this dotted line will represent the somewhere the weight of this particular slice will be there. Okay. Now, if the weight of each slice is to be resolved into the two components, that is normal and tangential, then the normal component will pass through the center of rotation O and do not have any driving moment on the slides. First, you need to understand how to draw all the slopes. So the first what you need to do is, first you need to draw this particular slope with a sum scale. This is a graphical method that you need to find it out. So that is why first you need to draw this particular slope with sum scale. So this is first I need to draw. Then I need to divide this particular slope into the number of slices. You can see this solid lines, which is a division of this particular slope into the number of slides. Once you do this, you need to find out the center location by means of dotted line. So I have plotted this center location by means of the dotted line. Now what you need to do is, for each component of the slope, so exactly what I am doing, first you measure this particular length. You can see this dotted length you first measure, and the same length you pass on here. So this will be the weight component. Exactly this length and this length will be similar. Similarly, this length and this length will be similar. So just pass on this length to at the end of the slide as a component of weight. Now this weight you need to resolve into the two components. One is the normal component which pass through the center of rotation. So you just put a scale here and draw a line which passes through this, and you can pass the line here, and from this line you draw the perpendicular component, which is this, which touches the tip of this particular weight. So you will get this and this. So this is the two components for each that you need to derive. Now you can see for each of the slices, you will see the locations. So this is a W which is always downward. Value of normal component which you are going to draw from this line O, which may be also downward, but from this you are going to draw the you can say the perpendicular component to the normal, and you are going from right to left. Here also you are going to right to left, but here somewhere you can see this is the weight component, but when you are drawing this, so this will be a normal component, and when you draw the normal component you are going from left to right. So here also there is a left to right. So there are certain slices in which you are going left to right, certain slices you are going from right to left. So that is, you need to see how you are going to resolve these components, measure this and draw this particular line. For example, I'm finding out what is the length here. So this length I'm reporting at each of the lining, and you will find this lines. Similarly, the tangential component, whatever the slice which goes in this direction, which is a driving side, which drives the slope in this direction, which is positive, and this is the resulting moment which I'm considering negative. So this will be the slope. If you have a planimeter, you might have used the planimeter in the surveying. You can actually find out the area with help of the planimeter, which is a one tool. By means of the experimental method, you can find out the area and you can use it into the equation. Right now, I'm just stopping here because this method, which needs more time, and probably we may not have much time. Again, we will discuss into the next lecture tomorrow or day after tomorrow. I will just post you, in which we will discuss this particular method in detail. So thank you very much. If you have any questions, please post in the chat box. I'm ready to answer it.